So, final video from section 7.5. This is one of those sections that gets 4 videos, which is, I think, the most any section has ever gotten. So can we solve the equation sine theta plus cos theta equals 1? Okay. Now, what some people would do is they'd say, oh, I know, I want sine of theta to equal 1/2 and cosine of theta to equal 1/2 because then they will add up to 1. Sine theta equals 1/2, for example, at theta equals pi over 6. Cosine of theta equals 1/2, for example, at theta equals pi over 3, and I've solved it. Nope, you've done nothing right. Okay. If the sine of theta is 1/2, the cosine of theta can't be 1/2 because remember, you always need sine squared theta plus cos squared theta equals 1, and that will be invalidated here. Don't just leap to saying, because one number plus another was 1, they must have both been 1/2. That's absolutely not true. Maybe it was 0.1 plus 0.9. Maybe it was -10 plus +11. Okay, neither one of those would actually work in this problem, but that's my point. Just because the sum of two numbers is 1, it doesn't mean you can immediately jump to knowing what they were. Okay, what you can do, however, is use existing identities to try to solve this equation. Now, none of the identities we have so far are immediately obvious. What you want to do, and this isn't clear why you would do it until you see it done the first time, is you want to square it. It's pretty uncommon to be staring at an equation and say, oh, I know what will make things easier, square both sides. But it does, and here's why. Squaring the 1 on the right-hand side changes nothing. It's just going to remain a 1. But squaring sine theta plus cos theta on the left will produce some very useful things. Okay? Namely, it produces a sine squared theta plus cos squared theta, which I can then cancel off with the 1 from the other side. Who saw this coming? Very few people. But once you've seen it done, you're like, ah, yes, when I square the left, I'm going to get a sine squared and a cos squared, which I can use to cancel the 1 on the other side. And now I have a nice product, sine theta cos theta equals 0, just by dividing by 2. And that's pretty straightforward. Okay? I can either have sine theta 0 or cos theta equals 0. And those have solutions that I know. They're exactly the quadrantal angles. Okay? 0 and pi have sine theta equals 0. Pi over 2 and 3 pi over 2 have cos theta equals 0. So the problem is we squared both sides. Squaring both sides of an equation introduces the possibility of something that didn't used to be true becoming true. For example, is 2 equal to -2? No, but if I square both sides, is 4 equal to 4? Yes. When you square both sides, you might have accidentally made something true that wasn't true. In other words, you've totally lost any information about plus minus because you squared both sides. So if you address an equation by squaring both sides, so if you solve something by squaring both sides, check the original equation. Because you might have accidentally lost equation. You might have accidentally lost information about plus versus minus. So go back and check that everything you found really is a solution. So for example, in this one here, if you plug in theta equals 0, you actually get a 1. Fine. If you plug in theta equals pi, you don't. You get out -1. You get out exactly this, oops, I mixed up plus versus minus. If you plug in pi over 2, that's cool. If you plug in 3 pi over 2, oops, that one wasn't really a solution. So 2 of these solutions are what are called extraneous. They're not actually solutions to the original problem. They were fake solutions introduced by squaring both sides. Basically, it's not just squaring both sides that introduces this problem. Anytime you do something to both sides of the equation, you have to worry, have I accidentally turned something that was into something true? And squaring can do that. Okay? Taking like the sine of both sides could also do this. So for example, is 0 equal to pi? Absolutely not. But the sine of 0 is equal to the sine of pi. Okay? Anytime you do something to both sides of the equation, there's a real big issue. Did I accidentally take something that was false and make it true? Adding a number to both sides never does this. multiplying by something doesn't do it unless you accidentally multiplied by 0. Okay. Multiplying by 0 does introduce extraneous solutions. Is 6 equal to 7? Nope. But if I multiply both sides by 0, now they're definitely equal. Okay. That's not something people tend to do by accident. Multiplying by 0 is kind of obviously silly. But in general, okay, multiplying by a number does not introduce extraneous solutions. Dividing by a number does not introduce extraneous solutions. But squaring both sides can. Okay, so be careful. Okay, so the only solutions were 0 and pi over 2. There's another way you can do this, and again, totally not obvious. Divide both sides by root 2. Oh, of course, duh. Who wouldn't think of that? Okay, I have this, which looks so much worse. However, the left-hand side kind of looks like the sum formula for sine, because 1/2 is, for example, the cosine of pi over 4. Not 1/2, sorry, 1 over root 2. And 1 over root 2 is also the sine of pi over 4. So what I have here is I have the cosine of pi over 4 times the sine of theta plus the sine of pi over 4 times the cosine of theta equals 1 over root 2. And I can now say by the sum formula, this is the sine of pi over 4 plus theta equals 1 over root 2. And then I can proceed from there. And that's what the book's going to do. Let me just clear out my writing so that we can see what they're going to write. Okay, so they called it an unknown angle. I mean, what angle has a sine and cosine of 1 over root 2? It's going to be pi over 4. Okay, so yeah. Get to it. The angle phi is therefore pi over 4. Yes. So as a result, we get this. Okay, the sine of theta plus pi over 4 is root 2 over 2. What are the solutions? Okay, now we have something. Sorry to go back and forth so quick. Now we have something that looks like a earlier in chapter 7 kind of problem. Find all solutions to the sine of something equals something else. So theta plus pi over 4 could be pi over 4 or maybe 3 pi over 4, which gives me theta could be 0 or it could be pi over 2. So those are our solutions. And again, totally not obvious that how you would do the problem, but once you see it, hopefully you're like, I guess, I mean, it worked. Honestly, for my part, the first one of squaring both sides, I would think of that. I would not have thought of this solution. Dividing by root 2, who would do that? Squaring both sides is a much more common way to approach this, although you do have to be careful about possibly introducing extraneous solutions. Okay, let's try another. Okay, suppose you want a sine theta plus b cos theta equals c, where a, b, and c are just numbers, but they haven't been given to you. What you do know, however, is that a and b can't both be 0. One of them, at least, is not 0. Either a is not 0 or b is not 0. Possibly both of them are not 0. What can't happen is that both of them are 0. Because, of course, if both a and b were 0, the left-hand side would just be 0, and I would have a very silly equation to try to solve. So this is pretty much related to the square both sides kind of argument. Try to divide both sides by root a squared plus b squared. Okay, I've divided everything by root a squared plus b squared. There is exactly one angle, phi, for which this term is going to be cosine phi, and this term is going to be sine phi. So I don't necessarily know what that angle is, but pretend I found it. Then I can rewrite this as a sum of a sine sum form. Okay, so we've just applied the sum formula for sine. So sorry, I should copy this from the previous slide. I kind of hate how the book likes to go to a new slide completely fresh, even if they're still working on a formula. So we have the sine of, and I can't really fit it anywhere. Hopefully we don't need this space. The sine of theta plus phi is c over the square root of a squared plus b squared. This is where we were. So if c is too big, if this numerator is bigger than the denominator, then you're asking for the sine of something to be bigger than 1, and that just doesn't happen. So we observe if this is going to have solutions at all, we had better have the absolute value of c less than or equal to the root of a squared plus b squared. Otherwise, that resulting fraction is either bigger than or less than -1 and won't have any solutions. Okay, however, if there are solutions, we take the arcsine of both sides. Okay, so either the thing we were taking the sine of is exactly that, or it's exactly that, but then shifted to be either in quadrant 2 or 4. Because remember, 2 or 3, sorry. Because remember, arcsine will give you the answer that's quadrant 1 or 4. So in general, if I have a given height I'm trying to get out, I'm going to get out the answer that's either in quadrant 1 or 4. How do I get the other one? It's by symmetry argument. If this is the result, this one is pi minus that. Okay. If the answer had been down here, and I had gotten out this height, how would I know this one down here? Instead of going down this way, it would be go pi plus that amount, but since this was negative, it's actually minus. Way, it's just pi minus the arcsine. Okay. So we have two possible solutions for theta plus phi. If you can determine the angle phi, let me clear out my ink, then you have solved this. This is a pretty abstract ending example to end on. I don't think it's something that's really worth stressing out over. I'm going to go back to where this example started, though, because let me erase my work. This dividing by a weird constant, I think, is as helpful as squaring both sides. If I square both sides, we get a squared sine squared theta plus 2ab cos theta sine theta plus b squared cos squared theta equals c squared. Now the issue here, when we did it before, we ended up with a sine squared and a cos squared, and we kind of canceled them out. But here I don't just have sine squared, I have a squared sine squared theta, and I don't just have cos squared, I have b squared cos squared theta. So I don't necessarily have the same amount of sine squared as I have of cos squared. So this technique doesn't quite work on this problem, which is why they skipped right to the divide by technique. Okay, but as I said, really, this last example I think is a poor one to end the section on. It's significantly harder than anything we're going to throw at you. Don't stress about it. Do, however, make sure that you can solve things from earlier in the section, especially the establishing identities. Okay. We only did, I think, one example in this section, but there will be many, many in the book. Practice those. It's the same technique as it was in section 0.4. You're just throwing your sum and difference formulas for sine and cosine in there. Make sure to practice those. The last 3 to 5 years, every midterm has had a problem that was established at the following identity, and almost always it uses one of the sum or difference formulas. I mean, there's going to be a practice midterm, you'll see, and one of them almost guaranteed will be establish the following identity, and it will involve a sum or a difference formula. So please, please practice those. If I tell you that problem is on the midterm, then you practice it and you get it right, you get points. I don't have to spend as long grading because they're all done perfectly. Everyone's happy. Okay, the midterm is going to happen, establish the following identity problem. I'm just telling you, it's going to be there.